dot equal to 0, then x mu dot would be some constant which we call as p mu, and x mu would be p mu tau plus another constant h mu. So you find that x mu and p mu themselves are the constants of integration, and so this part is somewhat similar to the trajectory of a free particle. And but in principle, if you like, one can even introduce more constants. Okay, but
I mean
in the coefficients,
yeah.
Here and
no,
here.
No, it's in front of XL or
X and L, X mu. Yes,
yeah.
you can. In principle, you can.
Yeah.
That's correct. Nothing lost.
So
And so yes.
the one.
So that means whatever calculations we do, but then I mean either need to be modified according to C1 plus C2, or one could take C1 equal to C2 equal to 1 as a special case, but one could even retain it. See, what we are going to do, you are actually very correct. In all the cases, you will find that we would separately obtain x mu L and separately obtain x mu R under different boundary conditions. So the total solution would always have to be obtained by summing them. So we could keep C1 and C2 as well.
In this case, one of the solution would correspond to some incoming radiation, and the other one to some outgoing radiation solution.
That I'm not sure. How do you want to say incoming?
So they really look like advanced time and retarded time solutions.
Oh, I see.
And we have the
I haven't.
yeah.
I haven't yet thought about it, but perhaps we could think about it. I could think about it. So far, I haven't thought about it in terms of the what you are saying. I haven't thought. But of course, I mean the most general solutions would have two constants like this. So C1 into this plus C2 into this. That's fine.
But we could just then drag the constant, for example, for XL, we could just drag the constant C1 into XL and then just redefine XL mu, P, L mu, and every alpha K mu to contain this C1, and then it would vanish. So it's actually a bit arbitrary to keep it or not. If we just drop it, like you did in the beginning, you still have the most general solution. Just not with explicit coefficients for the functions, but they can be implicitly contained inside the function. Due to having at every term inside the solution we obtained a constant coefficient, we can just redefine. So
I think that looks acceptable. That's correct.
yeah. So
Yeah. Okay. Is that okay? All right. Okay. So for the time being, let's drop C1 and C2, and let's now see what happens to these solutions. So let's first take the case of the open string, and let's apply Neumann boundary conditions. So at both the ends we take Neumann boundary conditions. Okay, and we know how these are defined. So these are, we say that 0 x prime mu equals to del sigma of x mu, and sigma equal to 0 and sigma equal to pi. At both the ends we apply Neumann boundary conditions, and for this, so x prime is 0. Okay, what we have done for the Dirichlet boundary conditions, these two ends were kept fixed. So the time derivative was 0, and here they were allowed to fluctuate or move around. So x dot was not 0, but then we impose that okay, let their space derivative be 0. So this is how we defined it, and this is all right. Now, so we would be taking the, let us take the space derivative of this, and so del sigma of x mu L, and this we first do at sigma equals to 0. So ls square by 2, we are taking space derivative, so we take derivative with respect to sigma, and so ls square by 2 p mu L, and the space derivative of the term involving tau vanishes, plus ILS by square root of 2 k not equal to 0, 1 by k alpha mu k e to the power minus I k tau plus sigma. And because we have taken space derivative of this, which means space derivative of this object, so this would be e to the power same thing times minus iota k. So here I should have, or let me write it here. Okay. I could write it like that. Okay. Very good. And then we take this at sigma equal to 0. So all this at sigma equals to 0. So this is the same ls square by 2 p mu L plus ls by root 2 k goes away, and if you like minus iota times I, this also gives me 1. So this times alpha mu k e to the power minus I k, and sigma is 0, so just down. Okay. Now I should do the same thing with x mu r, and this also I take the space derivative here. So this should be, I should have 1 minus, because 1 minus sign is now extra here because of minus sigma here. So I have minus ls square by 2 p mu r plus ILS by 2 summation over this. Now minus iota k I would get again out. So minus iota k by k times, now with this would be beta mu k into e to the power minus I k tau minus sigma. But now I have to have it at sigma equal to y. So that means I would now like to have it. Oh no, this is also, I am doing it only at sigma equal to 0. I am sorry, I have not yet gone to sigma equal to pi. What I have done is, we have obtained space derivative of the left moving component and then set sigma equal to 0. We are doing the same thing. We take the space derivative of right moving component and then we set sigma equal to 0. So we set sigma equal to 0. This will drop out from here. And so what I would have is this equal to,
Is the minus sign correct? In the
yeah,
ik over k?
because here you are obtaining its space derivative. So these are two terms. The space derivative of this goes away. Space derivative of this gets one extra minus sign here.
I mean the other one.
In this one,
Yeah.
because e to the minus ik into okay, you mean this, okay, so this should be this should have plus here.
Yeah.
Correct. Thank you. Because you get minus and one more minus, so you have plus. Thank you very much. All right. So, and now you put it equal to, so this now iota into iota, so here you have minus. This thing goes away, ls by square root of 2, and then this summation, and this kk also goes away, beta mu k e to the power minus ik into tau, sigma term goes away. All right, good. And so this is what you have, and now you can obviously write the I think I could do it here for the total solution. So I have to add these two, okay? And for adding up these two, this is del sigma x mu at sigma equal to 0 plus del sigma x mu r at sigma equal to 0. Now, so that means I have this and this. So ls square by 2 into b mu